All right, hello and welcome back. Today we're talking about rules of inference, and we're going to get started on the proof method for showing that an argument is valid. So again, I promised you a method for determining whether an argument is valid, right? Um, in a logic class, you do the truth table method, and you know that's one way to do it, right? And in some ways, it may be a little more foolproof. It's also pretty boring, right? You just have to and the longer the argument, the larger the truth table gets, and the easier it is to make a mistake, right? Um, if this is my critical thinking classes, I skip truth tables, right? Because it's a little boring. In my logic class, we did do truth tables, right? So that line is wrong. Logic class, right? But so here we're going to get into proofs. They can be a little bit more fun, I think. If you have a certain kind of brain, they're like little puzzles, and so once you get the hang of it, I don't know, there's a kind of enjoyment you can get out of doing these proofs and figuring out whether an argument is valid. So again, an argument is a set of premises and a conclusion, right? And remember our definition of validity, a valid argument is one where if the premises are true, the conclusion must be true, right? So what a proof does is prove that. It proves that the conclusion can be derived from the premises using only valid rules of inference. So we'll see a small set of rules of sort of inferences you can make that are guaranteed to be valid, right? So if you can get to the conclusion from the premises using only this special set of rules, then you can be sure that the argument is valid. Right? So what's a valid rule of inference? Well, it's one that if you start with true premises, you're guaranteed a true conclusion, right? And they're also simple. You'll see that they're kind of obviously true. You can also prove them to be always valid using the truth table method if you like. So the rules of inference we're using, we call them truth preserving, right? If you start with true premises, you're guaranteed a true conclusion. Now, if you start with a false statement, you can't guarantee a true conclusion will come out, right? But again, if you give them truth, they'll always produce truth. And you can stack them up, right? And this will be how we prove these arguments valid using the proof method. So again, the other nice thing is when we're just testing arguments for validity, we don't actually have to worry about whether the premises are true, right? That's an extra step. Now, certainly, if you want to know the argument is sound, you'll need to know whether the premises are true. But for now, remember, we're just testing for validity. We're just testing for a good, strong relationship between the premises and the conclusion. And these valid rules of inference let us do that. So we're going to use these rules of inference in proofs. Now, the text presents this very abstract notion of what a proof is. I don't expect that this will make a lot of sense yet. Once we get into practicing, it'll start to make sense, right? So these Greek letters here, this alpha 1, alpha 2, these stand for any statement, right? So the statement might be P, it might be P and Q, it might be if P, then Q or R, right? So this alpha on line 1 could be any statement that can be produced in our logic language, right? So a proof is going to have a set of premises that'll be statements in our logic language. That's what alpha 1 and alpha 2 are. Who knows how many it can have as many premises as you like, right? So that's what it says down here. Well, it might be premise n, right? It might be the last premise you're given at the beginning of the proof. Then you see over to the right on that fourth line there, a Greek beta. So that's just stands in for any conclusion, right? Again, it could be any statement in our logic language. It might be P, it might be P and Q, it might be if P, then Q or R, whatever, right? So all these alpha stands for statements in our logic language that are premises in the argument. The beta stands for a statement in our logic language that is the conclusion of the argument. So what a proof does is produce a bunch of new lines, and that's what the n plus 1, n plus 2, and so on are, right? And those lines can be derived from our premises using our rules of inference. And if you can produce lines and then finally one of them is beta, right, our conclusion, then you've just completed the proof, right? So in sort of normal English without the Greek letters, you've got a set of premises and you can create new lines, right, new statements in our logic language using only our valid rules of inference. And if eventually you can produce the conclusion, right, coming from the premises just using valid rules, then you know that the argument is valid. We'll get some more concrete practice with this soon, right? If that doesn't 100% make sense. So again, the proof shows that the argument is valid by showing that we can get to the conclusion using only the premises and the valid rules, right? And since these rules are truth preserving, right, they would never introduce falsehood, we can guarantee that we have this valid relation between the premises and the conclusion, right? So it's a sort of a truth bridge, I guess, between the premises and the conclusion. They're little, ladders in the I just switched metaphors to a ladder, right? But they're little rungs, right, or little steps in our truth bridge that guarantee truth, right? They're never going to lead us wrong, these valid rules. So what are these special valid rules of inference? I think you'll find them pretty familiar, actually. So the rules of inference have these Latin names, right? I'm not going to make you learn the Latin, right? Because you can abbreviate them. So you can just remember the abbreviations if that helps, right? If you I notice people's tongues kind of trip over the Latin and it's easy to confuse them. So here's our first two rules. They're called modus ponens and modus tollens in Latin. We'll call them MP and MT. Right? So what is MP? It's Latin for the manner of placing, right? And it goes like this. First of all, MP and MT, they only apply to conditionals, right? Well, that helps simplify things a lot. You'll see when we get into proofs, right? You're never going to use MP or MT on a statement where a disjunction is the main operator, right? So if we've got a conditional, here we've got P then Q, and if on another line, another one of our premises has just P on its own, right, the antecedent of the conditional, just sitting there on its own, we can validly conclude Q, the conclusion, right? Or sorry, the consequent of the conditional. We can put that on a third line, right? So again, if you have a premise with a conditional and you have another premise that has the antecedent on its own, you can derive the consequent on its own. So here's an example. This should be pretty familiar. If Nate is human, he is an animal. Nate is human. What can you conclude? Nate is an animal, right? That's just how, again, if-then statements, how conditionals work in English, right? If it rains, the streets will get wet. It's raining, the streets will get wet, right? Should be a very familiar form of argument, and it turns out that it will never introduce falsehoods, right? This is a guaranteed valid form of argument. So how might you use MP in a proof, right? So suppose you had these two premises, right? So here you've got a conditional. Notice the antecedent of that conditional is a compound statement, right? That's okay. You can still use modus ponens, right? So modus ponens doesn't have to be just P then Q, right? It doesn't have to, antecedent doesn't have to be an atomic statement. It's any conditional, right? So here the antecedent of the conditional is compound. It's A then B, right? That's fine. What we do have here is on premise one, we have a conditional. Premise two, we have the antecedent of that conditional. Our goal was to get to C, right? You can see over there on the right. That was the conclusion we were trying to reach. Well, it turns out we can reach that conclusion in one step, right? We already have the two premises we need to do a modus ponens. So we just say, okay, 1, 2, modus ponens, we can get C, right? And you see over on the right of line 3, we write down the two lines we used and the rule of inference we used. So we're going to have to practice this, right? It might seem tricky at first. You'll get the hang of it. I use different metaphors. Some of them click with people more than others, right? You might think of modus ponens as like a little machine, right? So you've got this conditional, and then if you feed in the antecedent, it spits out the consequent on its own, right? So a conditional is sitting there waiting for you to feed in the antecedent. So if you have the antecedent on its own line, you can stick it in there. Modus ponens, right, is the name of that process, and it always spits out the conditional, right? So that over on the right there where it says 1, 2 MP, we call that the justification. So every new line that you produce, right? So you would have been given just 1, 2, and the conclusion there. And line 3 is a line you would have added, right, in doing the proof. And whenever you add a line, you have to give a justification for how you were allowed to write C on line 3. And the reason you were allowed to write C on line 3 is because it follows from 1 and 2 modus ponens. So importantly, when using modus ponens, you can only use entire lines, right? So if you have suppose you had this proof you needed to do. right? So you had three premises and a conclusion. The first premise is a conditional. Here, the consequent is a compound statement, right? So you have if B, then A, then C, right? Suppose on line 2 you have B, and on line 3 you have A, right? So you're trying to get to C. If you were looking at this, you might be tempted to just use the A and sort of the second half of line 1 and say, oh, I'll just do a modus ponens there and spit out C. But you can't do that because A then C is the consequent of a conditional, right? You can only do modus ponens on an entire line. You can't just pick part of a line and say, I'm going to do modus ponens with that, right? So what would be the right way to finish this proof? Well, we do have a modus ponens we can do, but it's with line 1 and line 2, right? So line 1, we have a conditional. Line 2, we have the antecedent of that conditional. We have B, right? So with line 1 and 2 modus ponens, we could get line 4 here, right? It would spit out the consequent, and that is the conditional A then C, right? Now we have that on its own, and now since we have A on line 3, we can do a modus ponens with line 4 and spit out C, right? So lines 3 and 4 modus ponens would give us C on its own, right? So now notice, you created the new line, line 4, right, that wasn't in the original problem, and then you later used line 4, right, to produce a new line. That's fine, right? Because since you used a valid rule of inference to create 4, 4 is solid gold, right? You can depend on 4, so you can use that in further steps in your proof if you want. Okay, so that's modus ponens. This is the other rule that you can use with conditionals. It's called modus tollens in Latin. It's called in the manner of taking away. We'll call it MT, right? So what MT says is this: if you have a conditional, right? So again, this is the other rule that applies to conditionals. MP and MT are the only rules that apply to statements where conditional is the main operator. So if you have a conditional and you have the negation of the consequent of that conditional, right? So look, here we have P then Q, and we have not Q. If you have those two on any two lines, you can create a third line that has the negation of the antecedent of the conditional, here not P. So, for example, if I make my bed, I'll get a cookie. I didn't get a cookie, I didn't make my bed, right? If it rains, the streets will get wet. You look outside, the streets aren't wet. Okay, it didn't rain, right? Again, a pretty natural way in English that we use conditionals. But now now it's codified, right? This, in fact, it's a valid rule of inference, right? You can never go wrong using this kind of inference. If you have a conditional, you have the negation of the consequent, you can conclude the negation of the antecedent. So what about this one, right? Here we have a conditional, not P then Q, and I have the negation of Q here, right, on the second line. So that looks like I could do a modus tollens, right? I've got a conditional, I've got the negation of the consequent, and that's absolutely right. You can do a modus tollens. All you have to do is negate the antecedent. But since the antecedent is already a negation, you would get not P, right? Well, that's okay. We have another rule of inference called double negation, right? Double negation says anytime you've got two negations next to each other, you can cancel them out, right? Again, there's a Simpsons episode, right, where Homer is a food critic and Lisa is helping him write an article, right? And Lisa asks him, well, what did you think of the food at the restaurant? And Homer says, oh, it was not undelicious, right? And Lisa says, okay, it was delicious, right? So your English teacher is probably been telling you your whole life to avoid double negations, right? The reason your English teacher said that is because they're logically equivalent to just taking the two negations away. So just be simpler with it, right? So yeah, in logic, anytime you have two negations, you could get rid of them, right? Or you could introduce negations two at a time, and they won't change the truth value, right? So here, again, if we did this modus tollens, right, even though the antecedent is already negated, that's fine. We can negate it again, and if you want to, you can do double negation and change it to just P. So actually, there's a lot of different sort of pictures that all count as modus tollens, again, because they all count as having a conditional, negating the consequent, and concluding the negation of the antecedent. But it can go lots of different ways. So the top left is the original way I showed you. The top right is another way it could go, right? So here I've got a conditional if P then not Q. On another line I have Q. Well, Q is the negation of not Q, right? Even though Q here doesn't have a squiggle in front of it, it still is the negation of the consequent, right? Because the consequent is negated, so we can conclude not P, the negation of the antecedent. The lower left we just did, right, where you have the not P then Q and not Q on another line. We can conclude P, right? Here we skipped the step of the double negation, right? That's fine if you want to skip that double negation step once you get the hang of it. And the lower right is another way it could go, right? You could have if not P, then not Q. On the second line, you have the negation of the consequent, you have Q, and then you can conclude the negation of the antecedent, P. So all of these count as modus tollens, and you kind of have to get used to it being possibly showing up in any of these ways, right? But again, the principle is always the same. You have a conditional, you negate the consequent, you conclude the negation of the antecedent. Okay, so we have we have three rules, including double negation, right? We have two rules for conditional. So let's practice a little bit. So here's a proof someone might ask you to do. It's got 4 premises and a conclusion. So the first premise is a conditional, right? The antecedent is a little complicated, right? But it is a conditional. That's the main operator. The second premise is also conditional, kind of a simpler one, where both the antecedent and the consequent are atomic statements. Line 3 is yet another conditional. Here, both the antecedent and the consequent are negated. And then finally on line 4, we just have the negation of n, right? So that's what we have to work with. And our goal is to produce k using only the valid rules, right? So here are 2 general strategies. So we need to get to the conclusion, right, from these premises using only valid rules of inference. There are 2 general strategies for attacking proofs, right? One way is to just look at the premises and see if anything pops out as like a rule you could use, right? There's nothing wrong with that strategy. There's no extra points for like getting the most elegant or simplest proof. So if you just try stuff, create new lines, right, using the rules, then keep doing that and see if maybe you kind of stumble into getting K on its own. That's fine, right? That still counts. Or you can strategize a bit and work backwards, right? You can look at the conclusion that you're trying to get to, and then look at your premises and think, well, you know, if I were to get my conclusion out, what premise would I have to come from, right? What sort of rules might I have to use? And you can sort of work backwards and even make yourself a sort of wish list of things you need. And we'll practice both of these strategies. So let's use the bottom-up strategy first, right? So I'm trying to get to K. If I'm going to drive K validly from these premises, it's got to show up in one of these premises. And the only premise it shows up in is line 1, right? But it is locked up way deep in this conditional, right? It appears to be in the antecedent of the conditional, but it appears as itself the antecedent of another conditional, right? That whole antecedent is negated, K itself is negated, so getting K on its own, not negated, is going to definitely take some work. Right? But at the very least, we know in order to simplify that, if we had a rule that let us break up a conditional and get the antecedent on its own in some way, that would probably help, right? That would get us closer to getting K on its own. And we only have one rule that actually does that, right? It is modus tollens, right? Modus tollens lets us take the antecedent out of the conditional. We have to negate it, but at least it gets the antecedent on its own, right? Well, could we do a modus tollens with line 1? Well, modus tollens requires another line that has the negation of the consequent. What's the consequent of line 1? Well, it's M, right? So we would need the negation of M, and we actually don't happen to have that on its own either, right? But if you wanted to, you could jot that down and say, geez, if only I had not M, I feel like I could get a little closer to getting K on its own, right? And that could be your sort of next goal. How could I get not M on its own? Well, you have to look elsewhere. Where else does M show up? It shows up in line 2. It shows up as the antecedent of a conditional. Again, to get the antecedent on its own, we could use modus tollens, right? that would spit out M. It would spit it out negated, but that's actually good, right? Because we're kind of wanted the negation of M to do an MT with line 1, right? So maybe that's our plan, right? We got to somehow get not M from line 2. To do that, I would need the negation of the consequent of 2, right? Which would be not L. So I've already jotted down not M on my wish list. I would maybe jot down, geez, if I had not L, then I could get not M with modus tollens on line 2, and then I could get the antecedent of 1 on its own, and maybe get a little closer to K, right? So complicated, right? You can also work sort of top down, right? So you might just look at these premises, and you might look at lines 3 and 4, and so if I'm just looking at my premises and just thinking, well, how can I apply rules kind of without strategizing? And you can switch in between these two strategies, right? If you keep making notes from the bottom up and you say, okay, I've got not M on my list, right? And I've got not L on my list. Oh, I'm kind of stuck. If we look at like line 3 and 4, right? That looks to me like a modus ponens. We've got on line 3 a conditional. Line 4, we've got the antecedent of that conditional, right? So the antecedent of the conditional is not N. So if we did modus ponens with line 3 and 4, we could conclude not L. Oh, wait a minute, right? Not L was on our wish list, right? We wanted to use not L to do modus tollens with line 2. So our wish lists have kind of met in the middle here, right? And so now we could start adding some lines. On line 5, we could say not L, 3, 4 modus ponens, right? MP. We could then get not M with 5 and 2, right? MT. And then we could get not K then L, the antecedent of 1 on its own and negated, right? So, right, we said, oh, we saw 3 and 4, that just looks like a modus ponens, right? So we'll do it. And then we realize, oh yeah, we could, not L can help us with line 2 to get not M, and then not M gets line 1, the antecedent on its own, and it gets rid of that little negation sign, right? Okay, so now we have not K then L. What was our goal again? We wanted K on its own. Well, line 7, now we're a lot closer to getting K on its own, right? This is great. K appears as the antecedent of a conditional, right? The rule that gets the antecedent of a conditional on its own is MT, but what we would need to do MT with 7 is not L. Well, look at line 5. Line 5 is not L, right? So we can get K on its own with 5 and 7 MT, and we're done, right? So when you're first learning to do proofs, right, it's okay if you watched what I did and thought to yourself, I could never, right, figure out how to do that. That's fine. The first stage is just to, once I've solved it, right, look at what I did do and try to make sure you understand. For example, how was I allowed to write line 5, right? You were given 1 through 4, right? You were told your goal was K. So how did line 5 come about, right? What it says 3, 4 MP, but how did that work, right? Again, practice. The first goal is to just make sure you understand, okay, how is he allowed to write that on line 5? How is he then allowed to write that on line 6, and so on, right? So I was allowed to write not L on 5 because I had line 3 and line 4. Line 3 is a conditional. The antecedent is not N. Line 4 is not N, right? The antecedent of that conditional is sitting on its own. And modus ponens says if you have a conditional and you have the antecedent of that conditional on another line, then you can write the consequent by itself on the next line. That's exactly what I wrote on line 5, not L. Right, so that's MP with lines 3 and 4. How was I allowed to write not M on 6? Well, modus tollens, right, with lines 2 and 4. Modus tollens, sorry, not 2 and 4. Wait, not L. Yeah, sorry, 2 and 5. 2 and 5. It should have been. That's a misprint, right? So line 2 is if M then L, right? A conditional. Line 5 is not L, right? The negation of the consequent of that conditional, right? And so with 2 and 5 modus tollens, I can spit out the negation of the antecedent. Again, if it takes you a while even to see sort of puzzly how that's an example of modus tollens, compare it to the right? I recommend make yourself a little cheat sheet, right, of like all the rules, right, in their standard form. And then when I work through a proof for you, um, right, compare the move I made to the standard form and try to make sense of how that is in fact um, uh, an instance of that rule of inference. So again, line 6, there is a misprint, right? So that should be 2 and 5 modus tollens. Okay, and then line 7. So that is line 1 and 6 modus tollens. So what is line 1 and 6? Well, line 1 is a conditional. Line 6 is the negation of the consequent, right? The consequent of 1 is m. The negation of m is not m, right? And that's what I have on line 6. So if I have those two together, I can conclude the negation of the antecedent of 1. And since that was already negated, right, I can just pop that negation off. That's right. And so I get not k, then L on line 7. Okay, and then our last move, right, was to do another modus tollens. We had not L on line 5, right? And we can do modus tollens with line 7, which is because not L is the negation of the consequent of 7. And I can conclude the negation of the antecedent of 7, which is k. Now, at this point, you may be realizing he's throwing out a lot of big words really fast. Antecedent, consequent, negation of antecedent, right? This is why I said when we learned, again, the statement operators, right? That you have to learn those words, right? Antecedent, consequent, left conjunct, right conjunct. Those words have to be second nature to you. They're not going away in this class, right? And you can't just be, I mean, it's good to make a cheat sheet and make some notes so you can practice, right? At a certain point too, you're going to have to move away from the cheat sheet because as I've said over and over, logic is a skill. It's more like playing guitar or playing basketball than it is memorizing the, periodic table or something, right? So trying to do proofs when you don't remember what the word antecedent means, right, and you haven't really learned your rules of inference, it's going to be like trying to play basketball while trying to look at your notes on how to dribble, right? You won't be able to do it. So here's an important inflection point, right? If you're looking at this and the words antecedent and negation and consequent are like making your head swim, right? Go back and make sure you understand those words, right? And then come back and watch the lecture again. It's just a necessary point. The same in every logic class across all over the world, everywhere, right? Students have to learn these words and they have to make it second nature so they can move on to the next step. That's the way it is. Okay, here's our fourth rule of inference, right? So we've learned MP, MT, and DN, double negation. This one, disjunctive syllogism, or DS, applies to disjunctions, right? Or statements. What disjunctive syllogism says is if you've got a disjunction, right, on one line, and then on another line you've got the negation of one of the disjuncts, you can conclude the other disjunct on the third line, right? So again, you're very familiar with this rule of inference from English, right? It goes something like this. Nate will either eat lunch at La Fuente or Din Tai Fung. Din Tai Fung was closed and Nate didn't eat there. We can conclude where Nate ate lunch? It was at La Fuente, right? You can have soup or salad. Oh, sorry, we're out of soup. You're getting salad, right? When you have a disjunction and or statement, two choices, and then one of them is taken away or negated, the other one must be true, right? So this is all disjunctive syllogism means. You're used to it in your everyday life. Now we're making it formal and we're giving it a name. So so again, MT only applies to conditionals, right? But there are some parallels with DS because you're negating, right, one of the terms here. Here you're negating one of the disjuncts, and so that means that DS can take several different forms, right? So on the upper left is the form I just gave you, right, where you've got a disjunction, you negate one of the disjuncts, and you can conclude the other disjunct is true. It happens the other way. So it's not just the left disjunct that you can negate. You could also negate Q, right? So that's in the top right. So if you have P or Q and not Q, you can conclude P, right? So it's like the top left is like super salad. Sorry, we're out of soup. You're getting salad. The top right is super salad. Sorry, we're out of salad. You're getting soup, right? Either one you can negate and conclude the other one. Sometimes you get a negation where one of the disjuncts is already negated, right? You know, either I don't get paid or we can go out. Oh, I got paid, right? Therefore we can go out, right? So here the negation, the disjunction, one of the disjuncts was negated. So P is the negation of not P, right? So we do have the negation of one of the disjuncts on line 2. Again, we're looking at the lower left here. So we can conclude that the other disjunct is true, right? And again, like the top two, it's sort of parallel. So if I had P or not Q, and I had Q on another line, I could conclude P on its own. We also have two rules for conjunctions, right? So one we call simplification, right? So anytime you have a conjunction, you can just derive one of the conjuncts, right? This follows because that's what conjunction is. Conjunction, those are and statements, remember? It just says, here's two true things. Well, if they're both true, then either one of them can stand on its own as true, right? So Felix is a dog and Felix is Felix is white. I can conclude Felix is white, right? Felix is a dog and Felix is white. I could also conclude Felix is a dog on its own. Again, all of these rules of inference you've used in your everyday life, right? If you hear an and statement, you can easily just infer that one of the conjuncts is true on its own, because that's just what and means in English. So let's practice a little bit. We've learned a couple more rules. So here's a proof you might be asked to do. We've got our first premise is a conditional, right? The antecedent is itself a conditional. The consequent is not X. We've got a disjunction on premise 2, Y or Z. Here we've got a line 3 is a conjunction, right, of two conditionals. And then we want to get Y on its own for the conclusion, right? So how could we do that? What I typically do, right? I mean, again, it's up to you how you strategize. You can work backwards. You can say, where can I get Y from? Y kind of shows up a lot here, so that's not maybe the most helpful. But what I always do when I see a conjunction in one of my premises is I use simplification and break it up. And in fact, I use simplification twice to get the left conjunct on its own, and then again to get the right conjunct on its own. Here we're sort of like strategizing backwards. If you wanted to strategize backwards, you could say, well, the easiest way to get Y on its own is probably from line 2, right? And the other premises it's kind of tied up with a bunch of crap. So line 2 would be the easiest. You would need, right, not Z on its own to do a DS, right? And Z shows up in both the other premises too, right? But we'd have to do some work. Maybe if we got X on its own, right? But here's how I would tackle it, right? So first thing, I would simplify up, right, my conjunction on line 3, right? It's so easy to do. You only need one line. It's not like one of these two-line rules, right? Anytime you see a conjunction, just break it in two, right? So I'm gonna take the second half of that conjunction, just put it on a line. Typically, I would just go ahead and get Z then X and put that on a line too. Why not, right? Why did I take Y then Z? Because it is the antecedent of the conditional on line 1, right? So 1 and 4 is an MP, right? Maybe you don't see that right away. Like you just notice that 3 is a conjunction. You say, okay, I'm going to break it up. And then once you've broken it up, right, you say, okay, now what I can do. And maybe that point you realize, oh, actually I can use line 4, right? I can do an MP with line 1 and get not X on its own. Kind of cool. Maybe I'm not sure what not X is good for, right? But if I finish my breaking up of 3, right, and I see Z then X on its own, now 5 and 6 might pop out to me as a possible MT, right? Line 6, I've got a conditional, and I've got the negation of the consequent on its own. Notice here the conditional showed up later than the negation of the consequent. That's fine, even though, when I gave you the rule, it had the conditional first and then the negation of the consequent. It doesn't matter what order they show up. As long as they show up, you can use them together, right? So let's go ahead and do that, right? So 5 and 6 MT will give us the negation of the antecedent of 6, not Z, right? 1 second, I'm going to sneeze. Okay, so we're getting somewhere, right? We're trying to get to y on its own. Now remember, when we were initially strategizing, we thought, well, the easiest place to get y would be from line 2, right? If we could do a ds with that disjunction, if only we had the negation of the other disjunct. Well, now we do, right? Now we have not z on its own, so we can do a ds with line 2 and 7 and get y on its own, right? So again, this is the first time you're seeing these strategies, right? In practice, if you didn't initially know how to get to y immediately, of course not, right? But what I'm hoping you can get is if you see each of these lines and take it slow, go back over it, right? You can see what I did on each line and understand how I was allowed to do that, right? Let's go over it again slowly. We started with only 3 premises. How was I allowed to write line 4? Well, line 4 is one of the conjuncts of 3, right? And simplification says anytime I have a conjunction, I can break it up, right? And put each conjunct on its own. So I did that with the right conjunct of 3 on line 4, and that's 3 simplification. So how was I allowed to write line 5? Well, line 5 is a modus ponens in MP, right? Line 1 is a conditional. Line 4 is the antecedent of that conditional. MP says if I have those two things, I can put the consequent of the conditional on its own. And that's what not X is on line 5, lines 1 and 4 MP. Line 6 is just another simplification from line 3, right? I just took the left conjunct, and put it on its own. And having that, right, I was able with line 5 and 6 to do an empty, right? Because line 6 is a conditional. Line 5 is the negation of the consequent. And MT says whenever I have a conditional and the negation of the consequent, I can conclude the negation of the antecedent. Well, the antecedent of 6 is Z, right? The negation of Z is not Z. And that's what I have written on line 7. 5, 6, MT is my Finally, right, my last move is a DS. So I have a disjunction on line 2, Y or Z. On line 7, I have the negation of one of the disjuncts. And so DS says I can conclude the other disjunct on its own, right? So line 2 and 7, DS, I conclude Y on its own, and that was the conclusion that we wanted, right? So, eventually you'll get to strategizing once these rules of inference become second nature to you, but do try to at least be able to look at what I've done here and understand what happened on each line. Okay, another rule. So there's 2 rules for conjunctions. We saw one rule, which was simplification, which said you can always, anytime you have a conjunction, you can break it up and take any of the conjuncts and put it on its own. This is the reverse, called conjunction introduction. It says if you have any 2 statements on any 2 lines, you can always stick them together with a conjunction and make that a new line, right? And again, that just follows from the nature of the meaning of the word and, right? So if I have grass is green on one line, I have the sky is blue on another line, then of course grass is green and the sky is blue goes together, right? You know that Nate is a professor. Later on, you learn that Nate is a father. You can certainly conclude Nate is a professor and a father, right? Okay, so this ought to be fairly intuitive as well, right? That's what and means. All right, so junction introduction. This is another rule for that can use on disjunctions, right? So in my logic class, you need to learn this one as well. In a critical thinking class, I don't give you this one because it's a little less intuitive. So this is the second rule for disjunction. Notice we have 2 rules for conditionals, 2 rules for conjunctions, 2 rules for disjunctions. Right? So this one is called disjunction introduction sometimes, or DI. It's also known as addition, ADD. Either one would be fine for me. This says if you've ever got anything on one line, you can add a disjunction sign and add whatever the heck you want on the other side of that disjunction. Seems a little odd, right? It seems like you're just pulling statements out of thin air. I can start with P and just go to P or Q, right? Where did Q come from? Right? Well, this just follows from the meaning of the word or and the truth table of a disjunction, right? So again, for a disjunction to be true, only one of the disjuncts needs to be true, and then the whole thing is true, right? So, later I'm going to in and out or Jack in the Box. Okay, if I just go to in and out, it comes out true. If I just go to Jack in the Box, it comes out true. You only need one half of the disjunction to be true for the whole thing to be true, right? Well, that means if I've got something on a line, right, and I'm taking it to be true because it's showing up, I've derived it validly from or it's a premise, then I could add whatever the heck I want on it, right, to it. It doesn't matter if that thing is true because the first thing being true is enough to make the whole disjunction true, right? So Nate is human, therefore Nate is human or pigs can fly. That's a true statement, right? Because one half of it is true. Okay, so that's a disjunction introduction or addition. We practice it a little bit here, right? So here we've got a proof. So we've got 4 premises, and we're trying to get to the conclusion K and L, right? Okay, well, I see K, buried in line 3. I see L buried in line 4, but I don't see, we'd have to get those on their own, right? And maybe do a conjunction introduction to get that. Okay, so let's practice those a little bit. Here I have a proof. We started with only 4 premises, and the conclusion is a conjunction, K and L, right? So I know I can always build a conjunction with CI if I have each conjunct on its own. So if I could get K on its own and L on its own, then I could build K and L, right? Well, K shows up as the consequent of line 3. L shows up as one of the disjuncts in line 4. So I'm going to have to somehow get them on their own, right? So let's start with 4. How could I get L on its own? Well, again, it's in a disjunction, so it would probably be a DS, right? And I would need the negation of the other disjunct. The other disjunct is not A or G. So the negation of not A or G is just A or G, right? So how could I get A or G? Well, I have A on line 2, right? And DI/addition allows me to create a disjunction out of nowhere, right? So if I've already got A, I'll just create A or G, right, with DI. Now I have the negation of one of the disjuncts on line 4, and so I can get L on its own with DS. 4, 5 DS gives me L on line 6, right? Okay, great. I've got L. Now I want to get K, so I can jam them together with CI. So K is showing up on line 3. It's showing up as the consequent of conditional. Well, I have a rule that lets me spit out the consequent of a conditional on its own. It's MP. But what I need to feed in is the antecedent, right? The antecedent on line 3 here is C or D. Well, once again, right, I have this rule, addition, that lets me create disjunctions out of nowhere. And I do have D on its own on line 1. So I can create C or D from line 1 with addition or disjunction introduction. Okay, so that's what I did on line 7. I started with line 1, D, and I just added another disjunct and created a disjunction, C or D. And that's the one I needed because now I can do modus ponens with line 3 or 7, 3 and 7, and get K on its own, right? So that's line 8. Well, now, right, again, my strategy was to get K on its own, L on its own, and then put them together, right, with conjunction introduction. And here we go. I can do it. 6 and 8 with CI gives me line 9, K and L, right? So again, if you're a little lost, it's okay. Just watch it again slowly, see what I did on each line, and convince yourself that I'm allowed to write what I wrote on lines 5 through 9. All right, here is our last valid rule of inference. It applies to biconditionals. Again, if you're in the logic class, you need to learn this. If you're in a critical thinking class, I don't necessarily force you to learn this, although it's good to know, right? So we've seen what biconditionals are. They're just kind of two conditionals jammed together, right? So P if and only if Q is the combination of if P then Q and if Q then P, right? So biconditional is just a rule that says if you have those two conditionals, you can stick them together and make a biconditional. And it also says if you have that biconditional, you can break it up into the two conditionals, right? So here we have BC. If you have P if and only if Q, you can conclude if P then Q. You could also conclude if Q then P, right? That's the second version I have there. And then it also works in reverse. So if I have P then Q on one line, Q then P on another line, I can conclude P if and only if Q. So each of those is a version of the rule of inference biconditional. All right, let's just do a little proof using BC. So here we have 3 premises, right? The first premise is a biconditional, P if and only if Q. Our second premise is a conditional, if Q then R. And then our third premise is just an atomic statement, P. We're trying to get R on its own. So whenever I have a biconditional, kind of like when I have conjunctions, I just always use simplification to break them up, right? Even if I don't know what I'm going to do with it. I do the same with biconditionals. I'm just going to break it up, right? So I'm going to put P then Q on line 4 using line 1 biconditional, right? And it only takes one line for that rule. Okay, I've got this conditional. What can I do with it? Well, I might notice that on line 3, I've got the antecedent, right? So I can do an MP with 3, 4 and get Q on its own. What good is Q? Well, if we look at line 2 here, we've got another conditional with Q as the antecedent, so I could do another MP, right, with 2, 5, and I would get R on its own, and that was the conclusion I was looking for. So I've introduced all these rules. I've tried to give you a little practice or show how you would use them. Don't worry if you're a little confused at this point, right? This is a new thing, and it's a little hump the students have to get over. The next lecture is going to be more practice using doing derivations, right? So try to get these rules of inference in your brain, create a cheat sheet, memorize them, look over these proofs that I've done, and make sure that you understand how each rule made sense, how I was allowed to add each one, and you should be in good shape. And I'll see you again next time.